introduction. Good morning to all. The outline of this work are the introduction and the aim of work, the thermoelastic stress analysis, in particular used for the stress intensity factor evaluation during fracture mechanic tests, the automatic procedure proposed for the evaluation of the Paris law, in particular in martensitic stainless steels, and this application onto martensitic stainless steel as ASTM A182 grade 6NM and ASI 422, and then the conclusion. So, martensitic stainless steel are used in the engineering field application where corrosive and cryogenic environments are present in addition to high mechanical stress. So they have good properties for this particular application. In general, the principal methods used for the monitoring and the measurement of the crack growth are, as seen here yesterday, for example, microscopy, extensometer, ultrasound, X-ray, and in our case, thermoelastic stress analysis. In this work, we want to propose a new technique, a new procedure based on TSA technique for the continuous evaluation of the crack deposition and also the stress intensity factor calculation. So, in order to evaluate the Paris law, we propose this procedure on these two martensitic steel. So, in general, thermoelastic stress analysis is a non-contact technique that provides stress maps of a component subject to a dynamic load. So, in fatigue testing, we can relate some principal stresses to the variation temperature that occurs during the loading. This is possible through the thermoelastic constant K that depends only on the material. The typical setup of the thermoelastic stress analysis consists of a loading machine, an infrared camera, and a lock-in amplifier that is able to elaborate the signal reference from the load cell and the signal of the detector on the camera in order to obtain our analysis output, like the amplitude of the signal and the phase shift. The infrared detector of the thermocamera is able to detect the infrared flux emitted from the surface of a stressed body. So it's possible to relate the stress map of a component with the thermoelastic signal through a constant A. This is a calibration factor that depending also on the material, the kind of instrumentation, and the environmental condition of the test. In this image you can see the signal amplitude image obtained from a fracture mechanic test. From this relationship, it's possible to relate the thermoelastic signal to the stress intensity factor during the test. So, considering a generical point in this polar, system polar, we can determine this equation. In this work, we consider only the first mode loading. It's possible to replace in the previous equation the term R with the epsilon divided by theta. So, considering that the partial derivatives of the signal, the thermoelastic signal, in respect of the theta angle, it is this equation equal to 0 when the angle theta was equal to 60 degrees. So, in this way, we can evaluate the maximum thermoelastic signal as max. Then, if we consider a series of plot lines taken parallel to the crack growth direction, we can evaluate, we can simplify the equation in this equation, considering a linear relation through of the y coordinates and the square of the signal, thermoelastic signal mass, calculated in previously with substituting this angle. So it's possible to evaluate the stress intensity factor from this simple equation. In fact, in this graph, it's plotted the square of the signal, the maximum signal, versus the y coordinates. So, considering the p-value that we can determine from the graph, it's possible to obtain k. The calibration constant A can be is known in this application. In fact, we can evaluate this value from, for example, from the thermoelastic signal S on the gauge length area of the dog bone specimen. This is one possibility to determine this value. In fact, knowing the stress field in this area, it's possible through this equation and knowing the thermoelastic signal S to evaluate the calibration constant A. These are the values that we found for the two martensitic stainless steel. So we investigate 3 CT specimens for each material according to standard ASTM E647. The loading frequency of the test was 13 Hz, the loading ratio 0.1, and for increased emissivity of the surface we sprayed with flat black spray the surfaces. In this table, it is possible to see the delta P load that we use in the tests. So the setup provides a loading machine with a load cell with 100 kilonewton, a cooled infrared camera with a frame rate of 125 Hz at the full frame, but it's possible to have an elevated frame rate reducing the analysis area. The sequence acquisition with the RealMax software by FLIR, the data processing with the IRTA software by DES, the constant amplitude force was used in this test, and the acquisition each 2000 cycles, and the pixel dimension of 0.067 millimeters. So, this is the new automatic processor that we proposed. This part of the process was discussed yesterday in another work. So, in this work, we want to talk how to evaluate the Paris law through the thermal stress analysis process. So we have to save the thermal imaging from the surface of the stress body. We have to evaluate the amplitude signal image in order to evaluate the maximum thermoelastic signal. So we have an automatic detection of the analysis area in order to avoid this false signal that derive from the fixture grid. Then we can evaluate the stress intensity factor from plotting graph, and we are able also to evaluate the tractive position, with the phase signal analysis, and then we can evaluate the tractive load during all the test. So it's possible to evaluate the well-known Paris-Elkan law. In this graph, it's possible to see the comparison between the values determined by thermoelastic stress analysis and standard ASTM of the stress intensity factor during the test and the data in good agreement. In this graph, it's possible to see the results obtained for the ASTM A122 grade F6NM, and here there are the characteristical constant of the material determined. And in this graph, it's possible to see the the results, the Paris-Erdogan law determined in this case, and the constant material of ASI 122. So, in this work, the fractal mechanics behavior of two martensitic steels was studied using thermoelastic stress analysis. So it is possible to evaluate also the crack growth and the stress intensity factor continuously and in automatic way. We carried out 3 fatigue tests for each CT specimen, and the proposed procedure allowed to determine the Paris-Erdogan law of the material very quickly and present different advantages with respect to traditional methods. For example, a simple data processing, thermoelastic stress analysis data are simple to monitor, and this technique can be used to monitor the damage of real and more complex component subjected to a loading condition in general. So, thank you.